quiet, please. These men are making steel. More important work will go on in the world today, some of it of great urgency and high drama. Here, progress, if there is any, will come quietly, and it will be hard won. To make steel, you need iron ore, coal, and limestone, and creative thinking. The first three go into the blast furnace. The fourth goes into everything, for steel is whatever the customer wants it to be. How does steel become so many different things, starting as it does from crude materials gouged out of the crust of the earth? The question can be answered in a word. The word is research. It means search and search again. That's what goes on here in the laboratories of the Youngstown Sheet and Tube Company. It is a building devoted to the search for knowledge, and in it you will find strange and expensive hardware. The machines see what cannot be seen, measure what cannot be measured, compute what cannot be computed. But this is not to be confused with research. That is a function of the minds of men. The minds of men. The minds of men. The minds of men.
My point is, gentlemen, that we are well aware of the tremendous range of properties of steel which make it unique among metallic systems. There are certainly over 10,000 varieties of steel available. We must recognize that most of these grades of steel have been developed empirically. By that, I do not mean guesswork. I mean rather evolution backed by intuitive reasoning. To develop the steel products that will be needed for the future, we're going to need an even more scientific approach. We're going to develop the new steels as a result of greater fundamental understanding which we shall have of the materials to work with and their interaction in metallic systems. Gentlemen, our new laboratory is going to be one of the best equipped and have the finest tools in the world. The rest will be up to us. Now, gentlemen, let's get down to cases.
To make steel, you need coal. Not just any coal, but coal from which you can make coke. Not just any coke, but coke with specific properties and characteristics. This is not just a matter of digging and hauling. It is a matter of knowing. The research scientist prepares the sample for microscopic examination. What he sees tells him all he needs to know about the minerals, the carbon, hydrogen, nitrogen compounds that are present. The colors and patterns are as familiar to him as the pages of a book. Following the same procedure, the research scientists of the petrography laboratory examine everything that goes into the blast furnace. Coke, ores of various kinds, sinters, pellets. Because he knows the innermost secrets of all the materials, as well as their variations, the research scientist has data which will enable him to compute the best possible combination of materials to be charged into the blast furnace. A routine tool of the trade is the electronic computer. With it, he can simulate mathematically the sequence of events that will occur in the furnace. The computer makes iron in milliseconds. It tries out an infinite variety of combinations, compares them, and decides which is best. The optimum combination becomes the guide for the furnace operators. Not only materials, but the steel-making process itself is under the constant scrutiny of Youngstown research. Instruments which measure conditions at various levels in the blast furnace and its auxiliary apparatus are under careful observation. Efficiency increases with knowledge, and the rewards of knowing rather than guessing have been spectacular. There was the matter of thin tin. Standard practice has been to roll, to anneal, and to roll again. Research asked, is there a better way? It was first of all an engineering problem. Was it theoretically possible to achieve a 92% reduction of the material in one pass through a mill at rolling speeds of 5,000 feet per minute? Could the resulting product then be annealed using existing furnaces which operate at 1,000 feet per minute? The conclusion? Theoretically, it could be done. Now, the theory had to be proved. Days stretched into weeks. Work days continued far into the night. There were no sudden breakthroughs. Just sheer sweat and persistence. Each morning, the search began anew. In the laboratory, it was a matter of duplicating mill conditions on research-size equipment, making sample runs. Rolling. Annealing. Testing. And failing. Then searching out the cause of failure, modifying, and starting over. And over. And over again. And one day, the theoretical possibility became a laboratory reality. Tin plate stock could be reduced to size in one pass of the mill, and it could be annealed successfully. Still, nothing really useful had been accomplished, nor would it be until the laboratory results could be duplicated in the cold reality of full-scale production. Research teams moved their headquarters into the mill. Working closely with the production ready for a test run. No man could be sure if the multi-million-dollar machine could perform this kind of production miracle. This was research and calculated risk on a grand scale. That's the only size available in the steel mill. The test run was a significant victory. It proved that tin plate stock could be rolled in one pass. The result, however, was an extremely hard and brittle product. It remained to be proved that annealing would restore the necessary ductility. On the annealing line, there could be no small test run. It takes a mile of steel sheet just to thread the line. In operation, the sheet comes off the line at the rate of 1,000 feet a minute. If there were to be disappointment, there was bound to be a lot of it. And that's how it turned out on the first production run. Disappointment, and a lot of it. Back in the laboratories, the tedious detective work began again. What had caused the failure? How could it be avoided next time? There was a next time. Several of them. But in the end, a new product was born. Ductile thin tin made in one pass and continuously annealed. A significant victory for Youngstown research and the entire steel and canning industries. And to the research team, a source of gratification. And a reason for relaxing.
The problem, Carl, we've been losing too many pipe sales because we don't have the right items in stock. Now, as you know, we have a large inventory in the Southwest where we stock oil country pipe that adds up to nearly 100,000 tons. But it seems we don't have the right item, the right time, in the right place. Now, can your people help us serve these important customers in the Southwest?
I believe so, Bob. This should be a simple matter of mathematics and operations research. Could you give us a record, item by item, of the sales by yards for the past 5 years?
Yes, we can do that. As a matter of fact, we can give you the sales we've lost because we couldn't deliver.
Well, that's all we'll need. Turn the records over to us, and I believe we can help you.
And in this new problem, research went to work again. From the sales records, an optimum inventory was established for each item. Pipe production is now scheduled in accordance with this mathematical plan. The system has been refined over the years until today, 98.5% of tubular items requested can be delivered on the spot from stock available in the storage yards. But the greatest value of all, customer goodwill, even research cannot compute. To make steel, you need iron ore, coal, and limestone, and creative thinking. The latter is the hardest to come by, and by far the most precious. We use a lot of it at Youngstown, which is why perhaps they refer to us as a growing force in steel. And what of tomorrow? What of the steels to build the new worlds and give substance to the new dreams? The answer will be found on our research frontiers. Atomic power, plasma arcs, laser beams, high-temperature energy systems to produce metals continuously of unbeamed of purity and quality and capability. Quiet, please. These men are making steel.